Hello everybody, in this video I want to cover rotations in two-dimensional space, and we'll cover it with and without using any angles and trigonometric functions. As we'll see, the fundamentals of rotation is actually deeper and more foundational than the notion of angles and the concept of sine and cosine and trigonometric functions. And then after we do it without angles, then we'll later show how to convert that to using angles. Okay, so we have this coordinate space, this two-dimensional plane. We have this shape, this triangle, and we want to rotate it like that. So what we'll see is that this is not actually what we're going to do. What we are going to do instead is going to take this entire coordinate space itself and rotate it. And then we're going to re-represent this triangle in terms of this newly rotated coordinate space. Okay, so how do we do that? So a triangle, what's a triangle? It's formed of edges and vertices. We'll focus on the vertices in this case, and we'll focus on just this teal and blue one, and we see that each of them has an x and y coordinates. What does that actually mean? We can look at those as vectors if we want. That's like the duality of vectors and points, and we want to look at these two particular vectors at the center of the coordinate system of unit length, of length 1, and they are perpendicular to each other, or another way of saying it is they're orthogonal. So they're orthogonal to each other, and they have unit length, so they are normalized, and together they form what's known as an orthonormal basis. Okay, so what is an orthonormal basis? Is just these two vectors that every other point and vector in this vector space can be represented in terms of. What do I mean by that? I mean that with combination of some scalar versions, some scaled version of each of these two vectors. So what we see is that the numbers that we see in the coordinates of these blue and teal vectors, or blue and teal points that we saw, we actually treat them as scaling factors of these two orthonormal basis vectors, the purple and the green. And we can see that we just scale this up and down, and we can represent any point and any vector in this two-dimensional space just like that, just by using some numbers to scale up and down these two orthonormal basis vectors. Let's just see and take this example, this blue vector right here. It has an x and y coordinates, and again we're treating them as just scaling factors of the orthonormal basis. So as you can see, this is just showing that the vectors that represents the blue vector is just composed of a scaled version of the purple one and another scaled version of the green one by some amounts, and the amounts are the values of x and y, the blue ones. Okay, let's have a look. So we can rotate these vectors if we have different rotated versions of these vectors that are still unit length and are still perpendicular. They just point in some other direction. Okay, then we can represent new vectors and new points in two-dimensional space as scaled versions of these two new orthonormal basis vectors that are rotated. So if we use the x and y values of the blue vector that we had before, and instead of scaling them, using them to scale the original orthonormal basis vectors, the original purple and green ones, we use them to scale up these newly rotated ones. And as we'll see, we're getting the same vector as before. It's just rotated the same amount that this entire orthonormal basis is rotated by. Okay, let's have a closer look. So these two orthonormal basis vectors, they are vectors themselves, and we can represent them in terms of the original space, as you see here. So each one of them has an x and y, and again these x and y values are just scaled versions of the original purple and green vectors, and the same one we have for the other one, for the green one. And as we can see, we have two right triangles that are similar because they have the same hypotenuse, and they're basically 90-degree angle rotated versions of each other. Okay, so as we can see, because of that, the amount by which the purple vector has gone up is the exactly same amount by which the green vector has gone to the left, and the amount by which the purple vector has gone to the right is the same amount that the green vector is going up. So if we have just the coordinates values of the purple vector, we can just flip those around, and whenever we said x, we say y. Whenever we say y, we're saying x. And the last thing that we need is to just stick a minus sign there for the x coordinate, because we see that it's going to the left of 0. Okay, so we actually just need these two numbers, because then we can just regenerate the other one by just this flip that we just saw. So we can consider this to be a rotation vector, which means as it's a vector whose values we're going to be using to represent an orthonormal basis that is a rotated version of the original one. Okay, so this vector is just a rotated version of its original one, right? The one it's in with this coordinate 1, 0. So we can say that this vector embodies this rotation that we just see. Let's zoom up a bit, and let's see this vector that we just saw before, the blue one, and we can see it's still represented in terms of the original ones. And we can generate the green, just as we saw, by this coordinate flip. Now we have a rotated orthonormal basis, and then we can re-represent this blue vector in terms of this new orthonormal basis, just with these two numbers of x and y, the proper ones that we have. And as you can see, if we have different x's and y's for the purple ones, then we have a different rotation. Okay. How do we get this x and y in the first place? So we can use angles and sine, cosine, but we don't have to. We can use this rational parameterization of the unit circle, because as we'll see, all these vectors that are part of the orthonormal basis, they're all unit vectors, which means that they lie on the unit circle. Their coordinates as points lie on the unit circle. So we can use this rational parameterization of the unit circles that I talked about in my other video about circles. I'll have a link in the description below. Okay, so we can represent rotations like that. But so how do we compose rotations? So with angles, if we want to compose two rotations that are represented by an angle, so we have one angle representing one rotation, we have another angle representing another rotation, we want to combine those to the third angle that represents the combined rotation of both of them. How do we do this with this scheme? Okay, so we can use the exact same trick that we just did for the blue vector. We just apply that onto our rotation vector, right? So we take another rotation and we rotate the other vector representing the first rotation, and that's how we combine it to get a new rotation. So let's see how that goes. So as before, we have this second purple vector can be the rotation that we're applying, the second rotation that we are applying onto it, we can represent as another orthonormal basis rotation of this delta. Let's put it in the side here and rotate it to see it clearly. So this is the rotation, the delta rotation that we're applying onto the first purple vector that represents the first rotation. Okay, so if we'll just look at the x and y of the first rotation vector, first purple vector, and we look at these two new orthonormal basis vectors on the right, we can see that we can just represent the new purple one as scaled versions of this orthonormal basis on the right by the amounts represented by the coordinates of the first purple vector on the left. Right? So we're just taking these vectors on the right and we're scaling them by the coordinates of the purple vectors, the first purple vector. Okay, so let's have a closer look at this process. So each of these orthonormal basis vectors is in itself a vector, each of those, and they have x and y values. And again, these x and y values are represented in terms of the original orthonormal basis. So they are scaling factors of the original ones. Okay, so we can just reorganize things a bit. We can put the output on the left, and we can see that we have just vector scalar multiplication, two vector scalar multiplications. And we can represent that as vector matrix multiplications if we wanted to. Don't have to. Okay, and then we can see that this is just a rotation matrix that represents just the coordinates of these two orthonormal bases represent this rotation. Okay, this rotation on the right is what that rotation vector, rotation matrix in the middle, that's what it is. That's what a rotation matrix is. Okay, it's just these two orthonormal bases that are perpendicular to each other and have unit length, and they have some values. Okay, that's it. That's what a rotation matrix is. It's just these two vectors. Okay, now if we really wanted to, then we can say, okay, we want to represent this rotation with an angle, theta. Then what we see is, okay, we have this angle right here, and because they're orthogonal to each other, and these are the same triangle, just rotated version of each other, these two triangles. Then we have this theta here as well, and then we can see there's, say, this coordinate right here and this coordinate right here are just the adjacent, right? So it's the cosine over the hypotenuse. The hypotenuse is 1 in both cases. Again, these are unit vectors, right? So both of these are just the cosine of this angle. Okay, and then this guy, as we see, obviously is just the sine of theta, like this. And the last one, as we can see, is minus sine. So it's the sine because it's the opposite, and we stick a minus sign because we see that it's going to the left. And that's it. That's the rotation matrix that we saw in the very first slide. Alright, that's it. That's about rotations. If you enjoyed it, hit the like button, and if you want to be notified for further videos like that, you can subscribe to the channel. Thank you.